welcome to our NPTEL lecture series of flexible AC transmission system. We have already discussed shunt compensation. Now, we are going to discuss today the series compensation. So, series compensation is another important aspect of the shunt compensation. So, our presentation layout or the discussions will be on the following topic: the introduction of the series compensation. There are different type of the series compensation, that is series capacitor compensation, converter series compensation, and series compensator analysis and with its applications. Now, why we require the series compensation? We should start with the actually the limitation of the shunt compensation. Shunt compensation is ineffective in controlling the actual transmitted power, real power. It can actually control over the reactive power, as well as it can maintain the voltage regulation of the receiving end, but it cannot control the flow of the real power into the system. At a defined transmission voltage, it is ultimately determined by the series impedance, because P equal to V1 sending end voltage, receiving end voltage by X into sin delta. This is the equation. So, ultimately it depends on the X and the angle between the sending end and the receiving voltage, that is delta. So, that is the power transmission, and shunt impedance does not touch either this or this. Okay. It was recognized that the AC power transmission over the long line primarily limited to the series active impedance of the line. So, ultimately it is depending on the X. If you can control the X, then you can also control the flow of the real power with the transmission system. So, what it has been introduced, we have discussed in a wheel power in our first or second lectures, that is series capacitor compensation was introduced a decade ago to cancel a portion of the reactive impedance and thereby increasing the power handling capability of the power line, but it has got some limitations. The FACS initiative, because it will insert the capacitive volt impedance in gradually and with the mechanical switches, and thus most of the cases it leads to the subharmonic oscillation. The FACS initiatives has been demonstrated that a variable series compensator is highly effective in both controlling the flow of the power flow in the line and improving the stability. We shall discuss and we shall prove it. Moreover, it can be applied to achieve the full utilization of the transition asset by controlling the power flow in the lines, preventing the loop flow, and with the use of the fast control minimizing the effect of the system disturbance and thus reducing the traditional stability margin requirement. So, in a nutshell or in a one sentence, we can say that it is possible to enhance the stability limit with the series compensation. And the effect of the series compensation on these two basic factors determining the attainable maximum power transmission. So, we can see that we have discussed there is a thermal limit, there is a insulation limit. So, we require to check those aspects. So, we can use the thermal limit optimally by using this, actually optimally using the value of the impedance. And the steady state power transmission limit, transient stability, voltage stability and power oscillation damping also will be examined with the series injection. Now, the basic idea is to control the impedance. The basic idea behind a series capacitor compensation is to decrease the overall effective series transmission impedance from the sending end to receiving end. That means the impedance x. The V square by x sin delta relationship characterizing the transmission line of a single line system. And now let us consider a simple two machine model which we have already discussed in case of the shunt compensation, analogous to that shown for the shunt compensation, but there will be a series capacitive compensation in the line itself. So, there is a little change what we have discussed in case of the shunt compensation. So, what happened? See the circuit, this is the same two machine model. We will insert this extra capacitance here and we will split this inductance by 2, and this is Vs and this value is Vm and this value is Vr. So, thus note that the same sending end voltage and the magnitude of Vs equal to Vr equal to Vm. So, this is our assumption. So, we can state that, note that this same end voltage, that means receiving end voltage, and the magnitude of the total voltage across the line inductance is Vx, and Vx is given by from this trigonometry you can find it out what is the value of the Vx. So, this value essentially is the Vx. So, Vx is basically 2 Vx by 2, and Vc develops developed across the series capacitor. This results from an increase in the line current. So, what happened? Overall impedance decreases. Since the overall impedance is decreased, so current will increase. The effective transmission impedance E effective with the series capacitance compensation will be given by x, the previous with the uncompensated impedance, most of the cases will be minus, it will be minus xc, and thus E effective will be, you can take x common, this is 1 minus k, but k is xc by x and k can be ranges to 0 to 1. And ultimately we whatever same compensation we have seen, it will be there. This is Vs and this is Vr, and you can add up here or you can add up here, and ultimately it will be stretching. So, power angle on the new actually Vs and Vr will be this, and thus it will also increases the sometime the angle between this to sending end and the receiving end voltage. Now, that is what we said little bit earlier, that Vs equal to Vr, that may be equal to mod V, and the current corresponding to the real power transmitted by actually I, that is V minus delta by V0 by x. Now, it is being changed to 1 minus k. Thus, current changes to 2V sin delta by 2 x k minus 1, and we can write the sending end power. So, it is actually Vs into Is star. So, you have to multiply this V delta with this quantity. Ultimately, this quantity becomes, for the real power, become V square sin delta by x, and we have to equate the real and the imaginary term. Segregating the real and imaginary term, we can see that this value of the real power becomes V square by sin delta by x 1 minus k, and similarly the reactive power becomes V square 1 minus cos delta by x by 1 minus k. So, if k is 0.5, straight away you have actually twofold increase of your real and the reactive power. So, same way whatever power has been sent, that will be received. So, thus we can write receiving end power Pr and Qr, this will be given by Vr into Is, because Is will be same, because it is no shunt compensation is there, current through the all the element would be equal. So, same value you will get, and ultimately you get V square sin delta by x 1 minus k, similarly this one. Thus, what we can say, the reactive power supplied by the series capacitor will be this difference of the sending end power and the receiving end power, and so the reactive power supplied by this series capacitor will be 2 V square by k 1 minus cos delta by x 1 minus k whole square. So, let us see what is the implication of this expression. Now, this is the actually in x axis we have plotted the phase angle delta, and P and Q are plotted. So, this value corresponds to k equal to 0.4. So, you can see that for k equal to 0 corresponds to this graph with no compensation. If you make k equal to 0.2, you can have this graph, and if you make k equal to 0.4, you have this graph, and same way k equal to 0.4, you have, this is the power handled by this series capacitor. So, it will be QSC. Thus, what we can state, the relations between the real power and the series capacitor, reactive power QC and the angle delta is shown plotted at a various values of the series compensation, starting from value equal to k equal to 0, 0.2 and 0.4. It can be observed that as expressed, the transmitted power rapidly increases with the degree of the series compensation. Of course, and if you can if you make this k, theoretically it is possible though 0.9. So, you have a 10-fold increase in this transmission of the real power. The reactive power supplied by the series capacitor also increases sharply with k and variation of the angle delta. Now, converter type series compensation. This kind of compensation is called, actually it is analogous to the SVC in case of the shunt compensation. So, what you generally do, you generally minimize the value of the impedance, and thus you get the enhanced power handling capability, real as well as the reactive power handling capability of the line at the cost of the reduced impedance. So, current will be high and the thermal losses will be high. These are the few issues will be there. Let us see another type of the series compensation. So, this is called converter type series compensation. An alternate compensating circuit element may be investigated as an AC source voltage which directly inject the desired compensating voltage in series with the line. So, it will inject the voltage. So, same way it will manipulate the converter, and it will inject the voltage maybe in series with the quadrature with the sending end voltage, and ultimately what will happen, that power is given by V1 V2 by X. So, this value or this value may change depending on the position of the converter. The function of the series capacitor is to simply produce an appropriate voltage at the fundamental AC system frequency in quadrature in the transmission line in order to increase the voltage across the inductive light impedance. So, this is the function of this capacitor, and thereby it increases the line current of the transmitted power. So, ultimately it reduces the value of X and thus current increases. Ultimately, extra current is the cause of extra transmitting power. So, if you are transmitting 10 times more, that means you are sending 10 times more current. So, you would be touching the thermal limit very soon. For this reason, this is not an effective solution, because because of the high current flow through the system. Converter will inject directly the appropriate voltage at a fundamental AC system frequency in quadrature with the transmission line current, converter type series compensation for triple SC. So, this is the case here. For triple SC, it will inject the voltage in quadrature. Now, what happened? Let us see, this is actually the system diagram of this capacitor compensation. So, you have a SC, ultimately there you have voltage Vc, and ultimately you got the power V square XL minus XC sin delta. So, basic operation principle can be explained with the reference to the conventional series compensation with the related voltage phasor diagram. So, what happened, this is the angle delta, this is Vs and this is Vl, and ultimately what will happen, Vc will be in this direction and Vl will be in this direction. So, what we can infer from this actually this phasor diagram, the phasor diagram clearly shows that at a given line current, the voltage across a series capacitor forces the opposite polarity voltage across a series line reactance to increase by the magnitude of the capacitor voltage. So, this one was VL and this one was Vc, thus ultimately this became VL minus Vc, this voltage. So, what we can conclude for this phasor? While it may be convenient to consider series capacitance compensation as a means of reducing the line impedance, as we have explained previously, it is really means to increase the voltage across the given impedance of the physical line. So, because voltage increases and thus you may touch the insulation level. Therefore, what happened? The same steady state power transmission can be established if the series compensation is provided by the synchronous AC voltage source. So, we had a STATCOM that is had a synchronous condenser, and it can be actually replaced by a series injecting a voltage source. But FACS is a static solution, mind it, and we will not talk about any rotational solution that was previously used for the pretty long time. Thus, whose output precisely matches with the voltage of the series capacitor. So, Vq equal to Vc equal to J Ixc, ultimately we can write that value equal to minus Jk into XL, because you know that K equal to Xc by X, where the Vc is the injected compensating voltage phasor and I is the line current, X is the reference of the series, X is the reactance of the series capacitor, X is a line reactance, and where K is Xc by X, and it is a degree of compensation. So, thus by making the output voltage of the series output voltage of the synchronous voltage source a function of the line current, the same compensation as provided by the series capacitor is accomplished. In contrast to the real series capacitor, so this is a converter type capacitor, you can have a control over it. It is able to maintain a constant compensating voltage. So, you can control its voltage across the capacitor by the converters. and in the presence of the variable line current. This is the advantage of this. Actually, instead of the passive device, we have a converter control voltage source, or control the amplitude of the injected compensating voltage independent of the amplitude of the line current. So, that something depend on the load. So, you can vary the value of the VQ by the converter control technique. And for normal capacitive compensation, the output voltage lags the line voltage current by 90 degree, and it can be achieved by the voltage, and that can reverse simple by the local control action. So, converter type series compensations has the following characteristics. In this case, the injected voltage decreases the voltage across the inductive line impedance. So, ultimately net voltage become VL minus VC. So, VL decreases, and thus the series compensation has the same effect of the reactive line impedance compensation, but you got an advantage that you are not changing the value of the current, and value of the current and the VQ are the independent to each other. With the above observation, a generalized expressions for the injected voltage VQ can be simply written as actually V plus minus, depending on the kind of compensation you are doing. If you wish to reduce the voltage, you can also reduce the voltage, I by Im, why it is called unit vector compensation, where VQ is the magnitude of the voltage injected the compensating voltage, and this one is a chosen control parameter, and this is the basically gives you the direction of it. So, what happened with this type of compensation with the power transmission? Considering that sending end voltage is V angle 0 and the receiving angle is actually V 0, and the effective inductance is E effective. So, V square equal to E x q into sin delta, and thus it is V square by x 1 by x c sin delta, and here we will be actually replacing, because V x is a function of actually V q here. So, we can write the V square by x 1 minus V q by 1 into sin delta. So, thus you can see that this quantity plays an important role to control the sending and the receiving end power. So, ultimately, and VQ is a variable quantity and you can control, and thus you can control the power flow in the transmission line, and you are not touching the value of the current. So, this is the converter type series compensation circuit diagram. So, you have this similar two machine model. You have a sending end voltage V angle delta. So, thereafter you can assume that you have placed a series compensator VQ as a voltage source added in series. So, for this series compensator, and it will have a property of plus minus J VQ I by I by mod I, that is the unit vector, and thus the real power transmitted in this case is V square XL minus VQ by I sin delta, and ultimately this will be the phasor. So, effectively this voltage become VL difference VQ. So, this is a basic two machine system of the synchronous voltage source replacing a series capacitor. So, you can have the same control with a voltage source instead of having instead of actually reducing the value of the impedance. Now, what happened here? So, how let us draw the analysis what we have done little bit earlier for the impedance type series compensator. Now, it has an advantage. So, value of this VQ you can make it positive and negative, and it is actually delta by 2. For this reason, this is the expression of the power. You have a term added to it. So, assuming that value of the VQ is 0.5 or 0.707. So, what happened? You can see that even it at a 0 phase angle, you can transmit actually 0.7 root 1 by root 2 amount of power, and thus it will increase to the at 90 degree, close to 90 degree, almost 1.5 unit of power, and gradually it will come to 0 at 180 degree. So, straight away you get around 50% more power for 0.707 compensation, and also you can go to the negative direction. So, it has a huge power handling capability. So, minus 0.5 to almost minus 0.707 to 1.5. So, what we can conclude, the transmitted power and transmitted power PQ versus the transmission line angle delta relationship, and we have this following equation, and this will be the changed power dimension. What was initially just this value for VQ equal to 0, ultimately it can go up and down with the help of this series compensation, and it is a very superior compensation compared to the impedance change of impedance. Now, next course of action will be the stability. So, these are the, we will see that how the series compensation will actually enhances the few desirable features of the of this transmission line, that is voltage stability, improvement of the transient stability, and the power oscillation damping. We shall continue to our discussions actually with those topics in our next class. Thank you for your attention. Thank you.